So here we have question 4. This is dealing with water waves. It says a small sphere mounted at the end of a vertical rod dips below the surface of shallow water in a tray. The sphere is driven vertically up and down by a motor attached to the rod. The oscillations of the sphere producing traveling waves on the surface of the water. So we have here that waves are moving off in this direction, and they're caused by this oscillation to and fro. So obviously we've got transverse waves that are taking place here. Okay, so let's go further down to the question here. So the diagram shows how the displacement of the water surface at a particular instant in time varies with distance. Now this is interesting, it's distance, not time. The period of oscillation is 0.027 seconds. Remember that frequency is equal to 1 over t, so our frequency would equal 1 over 0.027. I'm sure we're going to use that at some stage. You'll probably also have to use this formula over here. So, having a look at it, what would be the amplitude? Well, the amplitude is always from your equilibrium to your maximum point, so that would be 1 millimeter. Make sure that you put in your units. The wavelength, well, the wavelength is 1 full cycle, so it goes up to there, and that's also in millimeters. So that works out, if you each small block is 0.5, so if there's 2 blocks it's going to be 6 millimeters there. The frequency, as we've just already worked out up there, is equal to 1 over 0.027. That works out to be about 37 hertz, and the speed is equal to velocity is equal to frequency times wavelength, and so if we put our wavelength into meters per second, so it's going to be 37 times 6 times 10 to the negative 3. We will get our final value, which is about 0.22 meters per second to the negative 1. Notice again, everything is to 2 significant digits, so that's why our answer there is in 2 significant digits. Good, so going on to the next part of this question. Going to go down. Now it says over here, the waves move from region A to region B of shallow water. The waves moves more slowly in region B. Well, that was nice of them to tell you, because shallow water, the waves move more slowly. The diagram not to scale shows some of the wave fronts in region A. So it says over here, with reference to a wave, distinguish between a ray and a wavefront. So basically you've got your ray here, and this is showing the direction that the wave is traveling, therefore the direction of the energy. So it's showing the direction of the energy. A wavefront is a line that connects all points that are on the same phase. So all of these would be in the same phase. This would usually be your crest that you'd have. So all those points, all the points in there are all at the top of their cycle. So I'm sure you, so let me just say it again, lines connecting points with the same phase, or they are all at the same point in the cycle. So going into over here, we've got the angle between the wavefronts. Let me just clean up this diagram a bit firstly. Clean it up a bit. So it says the angle between the wavefronts and the interface is 60 degrees. Now you've got to read this carefully. They talk about the wavefronts. So here you've got that's equal to 60 degrees there, as they've marked in the diagram there. Determine the angle between the wavefronts and interface in region B. So we're going to be looking at that. Now, what we have here is that if these waves are coming in, if I just extend this diagram down a bit, and I it's going in like that, and you've got a normal there. By symmetry, by the geometry of the situation, this will be 30. That over there will be 60 degrees. Sorry, that over there will be 60 degrees because this is 90 over here. This is 30 degrees over there, so that will be 60 degrees. So your angle of incidence is equal to 60 degrees. Now, if I extend that norm out, what's going to happen to these waves is they're basically going to lag behind. They're going to do something like this. They're going to lag behind. So you're actually going to get a change. It's actually going to change to something like that. I've exaggerated a bit there, but it's going to go in that direction. Maybe just let me use a black just to distinguish this here. So it's going to go something like that. Sorry about the quality of my drawing here. So looking at this over here, we are going from N2 as to N1. If we view this as N1, N2, because it's going slower, the N2 will equal, will be greater, it will equal the 1.4. And this is going to be the sine of theta 1 over the sine of theta 2. So basically we're going to have that's equal to 1.4. This this sine of theta 1 over here is going to be 60 degrees. So let me find some more space to work here. But so the sine of theta 2 will equal sine of 60 divided by 1.4, and it works out to that theta 2 is equal to 38 degrees when you find that angle. And because of symmetry, just like here, that will actually be your answer, because they're actually looking at the angle between the wavefront and the interface. So that just like this 60 equaled that 60, this 38 would equal this 38 degrees over there. Then it says, on the diagram, construct 3 lines to show the position of the 3 wavefronts in region B. I've done it here already. Please make sure that these connect here. You must make sure that these connect, and that these lines over here, use a ruler for them. They don't look like mine, and they need to all be parallel with each other. You need to make sure that they're parallel. Alright, so we have that. And then going further on here, we've got the last part of this question. It says here, another sphere is dipped into the water. The spheres oscillate in phase, so they are moving with the same frequency. The diagram shows some lines in region A along which the disturbance of the water surface is minimum. So we're getting destructive interference at those points. Now, just if you have a look here, I think you can see along there we are getting, if I just mark some of these points, you're basically getting from the one wave you got the line, and it's in the middle of the sort of in between the lines of the other ones. So I'll draw with red the other ones. So I've got the black dot is from the one source, and then I'll draw the red dot from the other. So it's basically happening that you're getting a peak meeting a trough, and so you're getting destructive interference. So the question is, outline how regions of minimum disturbance occur on the surface. Now notice you've got 3 marks, so you've got to put 3 points. So you need to explain how interference. So the interference occurs because you get the interference at a point, and you get the superposition of waves. So using that word, the superposition of the displacements of each wave, and these add algebraically, and in this case, and they cancel each other out. So they cancel each other out, and that leads to a zero or small displacement. Okay, so and that's because you've got the two waves are out of phase waves meeting. So that would basically get you 3 marks. And then it says the frequency of oscillation of the spheres is increased. Alright, so if the frequency has increased, it says state and explain how this will affect the position of the minimum disturbance. So what will happen with that, when you have an increase in frequency, when your frequency increases, when that increases, your wavelength will decrease. Because the velocity, which will remain a constant, is equal to frequency times wavelength. So if the one's increasing, the other must be decreasing. So therefore, you're going to have these this difference here. These will actually be these will be closer together, and therefore you're going to have them coming closer together. The position of the one and the other minimum will come closer. They will come closer together. Alright, so that's the end of that question.